Yeah, actually, I'm going to jump around a lot in time here and touch on a bunch of points which then will brilliantly come together into a coherent story, if I'm lucky. I'm going to start actually quite far back, and you, as many of you, of course, everyone knows Ada Lovelace, but you probably don't know that Ada Lovelace invented symbolic computing. She said, you only have to really read the first line here, which is the operating mechanism, and she's talking about Babbage's second machine, not the difference engine, but the, what was it called? Analytical engine, thank you. And she said that it might act upon things other than number, right? Duh, now. But you don't have to read the rest of this. But and this was quoted in Turing's Mind paper, where Turing, of course, invented the quote-unquote Turing test. Of course, he didn't call it the Turing test. Just like we didn't call World War I, World War I before World War II. So as I said, I'm going to jump around in time, and actually the first thing I want to do is jump actually ahead to 1971, I think it is. How many of you know about the Fireside Theater? Okay. We're all bozos on this bus. And Mike actually had loaned this to him and he brought it back to me. This is a, so basically it was an improv group and they put out records. You remember those, the plastic kind. Also were on the radio. And recently, I guess this is 2024, an academic, and this is an extremely academic analysis of Fireside Theater, blah, blah, blah. And some of it is very interesting if you're a Fireside Theater fan. But on page, actually, what page is this? On page 153, there's a chunk of Lisp code. And I'll pass this around if you want to look at it. And the reason there's a, well, some of you that know it, why is there a chunk of Lisp code on this page? So they may or may not have gone to sale, but they definitely saw the Lisp ELIZA, okay? Because there's an entire record called We're Bozos on This Bus, where famously the president is a computer and the guy introduces himself as Clem when he's asked his name, and so for the rest of the thing, it calls him Clem. One of the Firesign writers had apparently been shown the Deck 10, whether it was, I'm not sure what PDP it was on, Lisp in Lisp ELIZA, and that's kind of where they got that whole theme. Now, most of you, or many of you, may think that ELIZA was written in Lisp, and it was. That is to say, the ELIZA that became famous across the internet was written in Lisp, and in fact, that's a piece of it. Whoops. I'm also going to jump, because I'm jumping around randomly in time, I'm going to have to jump around randomly in my presentation. It's not actually, I just have a lot of slides to demonstrate things. So the ELIZA, whoops, it's actually above this. This is these are the deck tapes from the Lisp ELIZA, not deck tape, sorry, deck paper tape from the Lisp ELIZA, which I actually got from Bernie Cossel, who wrote it. And we also had the code, which I could show you if I could find it. Here it is. So this is a little hard to see. This screen is a little too small for this. I could make it bigger, you know, by pushing the button. It wouldn't actually help that much. Take it as given that, so this is his ELIZA, which we got a printout of, and we actually then had the Lisp community, a small part of the Lisp community, transcribe it in kind of, you know, overlapping pieces, and then it was written in BBN Lisp, and then we put a Common Lisp adapter on the front of it, and it ran. So in fact, you can pull, if you go to elizagen.org, you can actually pull off the Bernie Cossel's ELIZA from 1966, pull it down, run it in modern Lisp, okay? And it's just got about 20 lines. A line doesn't mean anything in Lisp, thank God, as opposed to Python. So maybe 20 little functions that are the adapter between the BBN Lisp and this. Now, I have a dog in this show. Is it a horse in this show, a dog in this show, or a horse in this race? Horse in this, is it the water go over the dam and under the bridge, or under the bridge and over the dam? Anyway, I have a pony in this, on this dam. Because now some of you may have had an Apple II or used a PC and you ran an ELIZA on that. Anyone remember that? This is an interesting question. Anyone actually have the ELIZA on one of the early PCs? I actually wrote that one. And it was written in BASIC, and it was written when I was 13. It's terrible, okay, as ELIZAs go, although ELIZA is terrible as ELIZAs go, but we'll get to that in a second. And the reason I wrote it, but it got published in GitHub at the time, which was called Creative Computing. And so it was only about 200 lines, and you could type it in, and apparently many people did, right? And there are thousands by now, thousands and thousands and maybe tens of thousands of knockoffs that came from that ELIZA. There are many knockoffs, not nearly as many, that came from the Lisp ELIZA because of course, Lisp is an academic language, right? Not a, not basic. So my ELIZA became the standard. And in fact, a funny story, I also was involved, although I didn't write it, I was involved in a friend of mine wrote the Apple II Lisp, which was called PLisp. And I wrote the manual for it, right? I actually don't, that's a long story. I don't have the contents of the manual, it's a PDF, which I didn't print out. But they did publish the manual as a book, which then was randomly translated into French. And my French family, my mother is French, my French family came upon this book in a bookstore that has my name spelled incredibly badly in the front of it because they translated it from that manual to this. Now, the funny part of this story, that's sort of funny, but only personally funny. The Lisp funny part of this story is that when we wrote the manual, my friend wrote the actual PLisp. Another friend of mine and I wrote the manual, Steve Backley. And we wrote it because we had built a teaching thing for Lisp as undergraduates. It did not have an ELIZA in it, right? But Steve Cherry, who wrote the Apple II Lisp, he created an ELIZA in Lisp for his Lisp, and it's actually in the back of this book because it went into the manual. And I was not involved in this. I just wrote the manual, left it, okay. He actually got his ELIZA model for writing it. He translated the basic ELIZA that I had written, that he had no idea, into Lisp, published it in the back of this book. So there's this complexity, this incredible complexity about, the sort of origins of ELIZA, all right? Now, many people think it was Lisp. And the reason that people think it was Lisp is that Bernie Cossel, who I mentioned, he actually did translate. He actually read the paper. Weizenbaum's paper was published in 1966 in CACN. And Cossel, they had just gotten a PDP-1, and McCarthy had put Lisp onto Lisp 1 point, whatever it was at the time, onto the PDP-1 at BBN. And Cossel said, this sounds like an interesting project. And he wrote what the academics came to have Lisp ELIZA in Lisp from the paper. The paper gave a script, I'll get to this in a little detail in a second, but not an algorithm. I'm sorry, a script but not the code. It had the algorithm. You didn't publish code at that time. It was very rare. First of all, it was too big. Secondly, what they were after was the algorithm, not the code. Okay, it's completely different now. So Cossel, of course, was then shortly after involved at BBN. What does BBN remind you of, if you're old enough? What was the origin of basically the ARPANET code, right? And so the imps were programmed at BBN. And so Cossel was part of the imp programming system. And so BBN was the first node on the internet, along with a couple of others. And so Cossel's Lisp ELIZA then became the ELIZA that everybody knew, all right? In the academic community, later on mine became the one that everyone knew in the PC community. Now, turns out, of course, many of you may know, ELIZA was not originally written in Lisp. Okay, it was written in a language called MacLisp. I'll get to that in a little bit of detail briefly in a second. Turns out we have that also. We went to the MIT archives and found the original code, and I will show it to you. Original ELIZA and MacLisp, here it is. We basically opened up part of Weizenbaum's archive, and there it was. Okay. At the top of this listing is a script. Looks like a big S expression, right? They had S expressions at the time for all of these languages. They didn't call them S expressions until Lisp called them S expressions. But anyway, this is the script, which actually not this particular script, but a script looking much like this, of course, appeared in the CACM publication. Okay, but the code did not, and the algorithm did, but the code did not. This is the actual code. It's written in a language called MAD, which is the Michigan Algorithmic Decoder, or it might have been the Madison Algorithmic Decoder, one of those Midwestern M computing hubs. I think it's Michigan. And Weizenbaum had invented a symmetric Lisp processor, which was SLIP, all right? And he was pushing SLIP, and so he actually, and you can actually kind of see it. There's list reads and lists and things like this. So there's all these lists. There's basically an API into the, it was a package that was imported into MAD. It's compiled together with MAD, more precisely. MAD is a great bizarre language. It's kind of like APL cross with ALGOL. It has these weird things in it, like that's an, so this is whenever, otherwise known as if. Remember, this is all on cards, so you don't want to type out a bunch of stuff because you'll make typos. So you can abbreviate all the long words. Now, why they used it whenever instead of if, which would even be shorter, but anyway, this basically says whenever some list thing is, equal to 0, blah, blah, blah. So it's sort of a cross between ALGOL and, yeah, there's some Fortran with the .e dots. Now, the early ALGOL might have had that, I'm not sure. There was, by the way, a Fortran list processing language called FLPL, which was also influenced by where I'm eventually going. We'll get to where I'm going in a second. By McCarthy, actually. So McCarthy, the little tangent, this whole thing is a big tangent. So McCarthy actually worked with, who's the guy? Galarter. Galarter is the Yale fellow who had his hand hurt by the Unabomber. David Galarter. His father, as it turns out, wrote FLPL under advice of McCarthy. At NYU, I believe. And so, or no, whatever the NY that's in the middle of the state is, a famous one, and it'll come back to me. And McCarthy went, Fortran kind of has functional structure if you just put a lot of parens around, speaking of paren matching, then you can like call Fortran in a sort of functional way. What does Fortran not have? Do you know? Recursion. Fortran does not have recursion. In fact, we're going to get in a second to the first recursion language. All right. So SLIP was this thing that McCarthy was pushing. It was a competitor exactly the same time as Lisp. This was in the early 60s. By the way, I was born the same year Lisp was born. You can now compute I was going to write, one of the many books I have written in my head is called My Life with Lisp. Because we were born at the same time, grew up at the same time, and in any case, none of these is a real book, except in my head. So I'm actually going to go back before Lisp to the influence of all of this. Okay, so let me tell you, I should thank people before I forget to thank people. Somewhere in my original, that's the the GitHub of the day thing. Oh, here it is. Sorry. Like I said, I'm skipping around in here and I should thank. So I run in the sense of I founded, in the sense of I pushed the buttons to create the RetroAI Discord server. You're all welcome to join. If you can't find an invite, let me know. But I just wanted to say I think that's a permanent invite. All of these folks are involved in all the kind of stuff that I'm talking about. Now, this was the team that essentially found the ELIZA, analyzed the code, fixed the code, and Rupert and a few of us made it run. Okay, and so now I'm going to do, given our hardware situation here, I'm going to take my life in my hands here and try and do a few live demos. All right, I'm going to show you the original ELIZA. This is CTSS, which was the operating system running on the 7094 at MIT in Project Mac. This is live, by the way. Running on a 7094 simulator, which is actually in the other window. And I've just telnetted into the 7490 simulator. And you can say, ELIZA, it's running on, so it's running on 7490. It's the actual CTSS, almost bit for bit pulled off the tapes, right? So the 7094 simulator is so good that you can just read the tapes off, run CTSS. There was of course, there's always a little IO thinking you have to do, okay? Oh, sorry, CTSS is the world's first time-sharing system. There's a little argument, but basically, it was the compatible time-sharing system. Some of you may have heard of the incompatible time-sharing system. So the compatible time-sharing system, if you were at MIT, the compatible time-sharing system was the first time-sharing system. I don't know what, it's compatible with Multics. Right, yeah, Bash, okay. And it ran on the 7094, which was a slightly modified 7090 at MIT. There were actually two of them, one at Project Mac on the 9th floor of AI, of the building at Tech Square, and the other one was over in the admin building. But anyway, CTSS was the thing that was being used here. And then what we have is we got mad and we made mad compile from the original tapes, basically. We got slip to compile into it, which was no simple feat. Now the Fortran slip was published. The mad slip we just kind of had to get. And then you can say R ELIZA. We had to fix the code. This is the original ELIZA really running. This is the whole stack down to the, the OS X base. Well, I guess you can, the 7094 simulator is modern too, but everything else above this is the original code. Now you have to tell it the script. The scripts were numbered. Please tell me your problem. I want you couldn't actually backspace at the time, of course. I want a pony. That's the original ELIZA doing its thing. All right. Thank you. And actually, I have to say, Rupert Lane and Anthony Hay and Art Schwartz had a lot more to do with it than me. But in any case, and we actually have, again, I'm skipping around to my thing. If you're interested in more of the details of that, we have a paper that just came out as one of these anecdotes in the IEEE, whatever, the vintage computing journal. Okay, you can read all about, it always comes down to a 1-bit error somewhere, right? And it did. It was like a lot of work. It was almost 6 months worth of work to get, all together to get all that going. All right. But I'm actually not here to talk about ELIZA and Lisp. All right. Rafe's talk was what did he say? It was a request, a call to action. Mine is a cry for help. All right. This was the first basically major project. So what we're after in the RetroAI group is actually reanimating the original AIs. All right, and as far back as we can get. And the original AI, I mean, it kind of depends who you ask. You can argue that Samuel's checker program, might have been that. Okay, but the ones that I'm after, because I happen to have been a student of Simon and Newell, all right, at CMU, is the IPL series of AIs that were the first heuristic programs. Okay, again, it depends what you call heuristics. Samuel's checkers program was probably considered heuristic. It's another long story. What happened is Simon, Newell, and Shaw at Rand in the early 50s. Now remember, Turing's paper was only published in Mind in 1950, okay? By 1953, Simon, Newell, and Shaw were writing cognitive models on the Johnny-act, which was this gigantic, as you can tell, von Neumann style, although in my opinion, you should call it Turing von Neumann style, because Turing really invented stored program computer. That's what a universal Turing machine is, right? The Turing von Neumann style machine, the Johnny-act was one of these, hand-built tubes and wires, 50 tons or whatever it cost, or whatever it cost. God knows what it cost, whatever it weighed. And it was probably the cost of an iPhone at the time, but that would be $100 million now. This was written on the Johnny-act, and they invented this language. Newell, I think, is the genius behind all of this, personally. Simon really was a psychologist. He wanted to do cognitive modeling, right, which, essentially was the original AIs. So the original AIs were cognitive models, not AIs, kind of fine line. And so Simon wanted to do cognitive modeling. Newell invented this, fall off the stage, invented this language called IPL. All right. IPL was, I'll show you some of it, and I'll actually show you to it running. IPL was imagine the assembly language for a Lisp machine. Okay, essentially. All right. A stack machine with intrinsic symbolic computing. All right. Intrinsic stack operators, intrinsic mapping. And I'll show you much more about IPL, because what I really want to talk about is IPL, and that's kind of my cry for help here. Is I'll show you where I've gotten in bringing IPL back. So I have not been able to find that the maybe best thing to say is, well, we've got a CTSS. We were able to run CTSS. Why couldn't you just run IPL-V? Right. By the way, it's IPL-V. IPL-V was the only version of IPL that was actually public. Okay, it was IPL-1. God knows when that was. They probably didn't call it IPL-1 like World War I. But, IPL and then IPL, 2, 3, 4 were internal to RAND. They actually published IPL-V. There's a fantastic manual. Unbelievably detailed manual, like the most, it like has problems and things, right? Okay, I'll show you some of this. I did try, actually Lee tried originally, just feeding the manual to an LLM and saying, write me an IPL interpreter. Okay, and it didn't work, as you can imagine. But actually the main reason, I mean, I'll get back to that because I do use the LLM to do parts of this, but you can't feed it the whole, part of the reason you can't feed it the whole manual is that OCR is so bad. And so, you know, it's just the tables are OCR'd like this way and that way, and you know, it's just a disaster. Now, Rupert, by the way, to get the ELIZA working, and actually to work on this other project, the LT project. So LT is the Logic Theorist, which was the first sort of big AI. And what it did was, so the Logic Theorist, written by Simon Newell and Shaw in probably 1955 or 6 was the first publication of it. What it did was it basically proved 3/4 of what's in Principia Mathematica, all right, mechanically, okay? And it probably could have proved all of it. I just kind of didn't get around to it for some reason, I don't know. There might be a more technical reason, I'm not sure why I couldn't do that. But basically it's a theorem prover, right? Symbolic theorem prover, written in this horrifically terrible language, right? Instead of parentheses, you have the following. You have, remember, this was all cards, not in addition to being ugly. So there was, of course, since it was cards, there was an IPL card form, right? And you have names and symbols and these PQ things. So I'll get into a little bit of this in a second in links. Okay, every program, everything in IPL was a list. Right? Remember, this is mid-50s. This is before Lisp was even thought of. Okay, Lisp was influenced by this, of course. All right. So if you have a list, if you have a program, here's a program in IPL. I'm not sure how, actually, you can probably see this one better. Now, that, well, it's a little too small. Well, if I slideshow, it'll be a little better. So, yeah, that's better. So what's going on here is, that's a symbol. Everything in this column and this column are symbols. It's a purely symbolic language. Okay. In fact, they had to hack numbers in the side. These are local labels. All right. So somewhere there's a go to 9-1, like that. That basically says on false, go to 9-1. Or it might be on true. I can't remember. Actually, I'm going to pass this around. The PQs are the most important part of this. So this is my cheat sheet when I'm working on this. I have to keep a cheat sheet around to understand what the fuck's going on. So let me read a little bit of this to you, and I might have to look stuff up. Everything with a J is a call to an external function. Not external, I mean to a, you know, to a function. I'll get back to what those functions were in a second. So this thing says call J9, and then when you return, call J34. All right, and you're going to go, what the fuck are J9 and J34? Well, that's an excellent question. And the answer is, I'll get into that in a second. You basically have to know. So there's a giant IPL cheat sheet, you know, somewhere else on my slides that actually gives you what these are. You get to know them after a while. And of course, if you were Simon Newell and Shaw and all these folks, you basically memorize it. But like one of them is car and one of them is coder. And they only had like 6 characters here to put the things in because all BCD code, right? So they had 6 characters, and so they decided to call all their J's. The other things are actually references to the stack, right? To basically stackable objects. So these are stackable symbols, unless it's, so that of course is a pointer to here. So the way this is internally represented is as a list. This is the list header, the list name, okay? And implicitly this link, unless it has something different, is a pointer to the name of the next address. Right? So you could actually read these as lists using the language. So it was meta of its own. It was basically entirely meta. You could write, I don't think anybody did, but you could write a macro processor on top of this. Right? Oh no, actually somebody did. I'll show you in a second how they did. Sorry, they did write a macro processor. So essentially what this is saying is like, when A0 is called, call J44, then go here. 60, what the fuck is 60? 60 is set the symbol W1, whoops, I was there, W0, and to whatever J44 returned, which is going to be a symbol, and push W0 stack, okay, etc. So all these things do stuff either to a test bit called H5, and then these things test the test bit. So 70 says branch to symbol name if H5 minus. So branch to 9.1 FH5 minus, okay, etc. Now, a lot of the work is done, so mostly this is processing the stacks, is pushing stuff, pulling off the stacks. All the list processing is done in these J functions. So you might say, well, the J functions were just assembly crap, and some of them were, the low-level ones were. However, many of them were, as you can imagine, written in IPL. So this is Simon's J's, Herb Simon being one of the guys who worked on this, who designed it from the early on. The computer history is some random person, Alex Bochenek, sent a box of cards to the Computer History Museum called Simon's J's. These are Simon's J's from Rand. They are the J functions written in IPL. Right? And actually, I'll show you a slightly better picture. Oops. Wait, this is my stuff. We'll get to my stuff in a minute. Right, so here's J77. Whatever J77 is, okay? By the way, Simon's J's have no comments. This is the version of J77 that came from the manual. So I wanted to, oh, and it turns out a fellow named Aaron Steffrand, anyway, published in 1963 a recoding as an educational project, a detailed recoding of the Logic Theorist in IPL-V. All right, and actually I'll show you that. Steffrand, see, this is where I'm getting into. There we go, Newell, Steffrand, 63. This is the logic theory machine, and he has, and by the way, this is greatly detailed. It has flowcharts for like every fucking piece of LT, which is thousands of lines of IPL, and I'll show you the actual code in a minute. And at the end, the second half of this entire thing is every line of code. All right, whoops, I'm not even up to it yet. This is the logic theory machine in IPL-V. All right. So my goal here, like ELIZA, is to run this. All right. And I'll show it to you running in a minute. Now, to get from here, remember, we did not have an IPL-V interpreter. Actually, we had one that did not work. All right. We had, in fact, it was on another 7090 simulator. It would not run this. All right. It ran a simple demo that I'll show you in a second. Okay, but it didn't run this. But the first thing they had to do was actually get it into something we could run. Whoops. So remember I said that Rupert Lane had written something that he has this great hack, by the way, which is public now, that OCRs code from PDFs, which is actually extremely difficult. All right, uses LLMs and all kinds of Python this and all kinds of visual crap, but it works. Okay, and you can now put this thing in and get a fairly respectable OCR of the actual code in the columns, which OCR completely fucks, right? We put that. Actually, we hand translated it, and then he finally got his thing running, and we found many errors. We've been finding errors. You know how you like write a paper, and then you read it, and then the editor reads it, you read it, it gets published, and it still has errors in it? Right, so this is like that. Okay, but I'll show you where it ends up. It ends up in here. So this is the LT transcribed, all right, into basically a Google sheet. All right, and then what we do is, and there's a bunch of complexity in here, like I have code in the Google Sheet that tells you what the PQs do, so you can read this. Notice LT actually has a passable number of comments, thank God. Then what we do is we pass that through, and here's where the demo part is going to be a mess. So I'm going to close ELIZA. By the way, when I stop this, what it's going to do is output in S expression the entire script. And the reason it does that is because the old ELIZA, another tangent, actually had a teach mode. You remember ELIZA is like Eliza Doolittle, which, Eliza Doolittle was taught by some, white British guy to speak English, speak proper English. And so you could actually teach ELIZA, Weizenbaum. There was a teach mode, which was in the original ELIZA, was never published. Okay, we found the code. I can run it actually in the IEEE paper. I show you doing it. So it has to output what it was taught. So you can output that to a tape, or you can just have the screen. That's actually a well parenthesized. If I had a run checker, hopefully it's a well parenthesized block of giant code. Okay, so I'm going to stop this and go to the. Oh, see, I logged out. By the way, CTSS did not have a year. You had to manually go into CTSS and hack the year when they went on January 1st. So it doesn't know what year it is. Well, it knows. I mean, it thinks it's 1963 or something. All right, so I'm actually going to kill this also, and kill this. This is my cheat sheet. Here we go. So this is. So this is, by the way, all this stuff is public on the actual GitHub as opposed to in creative computing. So this is so IPL-V and LT, and what I do is I create LIPL-V, which is basically just wrap parens around everything in the spreadsheet. Okay. This is the best thing about Lisp. The best thing about Lisp is you just, there's a phrase, wrap parens around it, okay? And then just load it and then figure out what to do. So I wrap parens around it and then figured out what to do. And the way I figured out what to do is, remember I said there was this great manual? Newell's manual is amazing. Here's the manual. It has everything that you could want. Detailed descriptions of the list structures. Actually, I'm looking for one particular thing. Actually, I think I have it in my, be easier to get from my presentation. So it has in it, oh, that's the Johnny Act while I'm finding this. Here it is. This is the interpreter. All right, it's called that flowchart of the interpreter. All right, so I started there, and I wrote, oops, bunch of Lisp code. Here's IPL-V. Oops. Oh, it's right here. It's the top level. This is the interpreter. Okay, and it's called IPL. Oops, don't want to do that. It's called IPL-eval. And you start IPL-eval wherever IPL. And this actually has the same names as the blocks in the flowchart, right? And it's just a big, it's not even that big a chunk of Lisp code. It's a couple hundred lines with a lot of comments. And it runs IPL. I'll show you this running in a second. Okay. And the reason I wanted to do this, you say, well, why didn't you just work on fixing the interpreters that are out there? And the answer is, I actually care more about IPL-V. I really wanted to kind of understand IPL-V, not just run it. Okay. Running it is, that's interesting, but it's not really having an in-depth understanding of what's going on. I wanted to understand the machine. What was in Simon and Newell's and Shaw's head? And, both in LT, but also in IPL-V. Right? So I wrote my own interpreter, and where there were J functions, sometimes I use the actual J's, that's Simon's J's, but sometimes I actually have a macro called defj. Now I manage that where, you basically write a Lisp version of the J function. Oops, and here they are. So J1, J2, etc. Right? And some of them recursively, there's a thing called J100, which is a generator. It's basically mapcar. And it takes a list and it calls a subfunction that you hand it as on the stack as an argument. The arguments, of course, are handed out on the argument stack, right? So you push the argument stack, you call J100, and it runs through. And one of your arguments is a pointer to the function that you want to call, right? And it runs them, and then it gives you usually, it can give you a set of results if you make it, but it usually just gives you I got through everything or I didn't signal. And then you can branch on that or do whatever you want. I wrote these things in Lisp, and because they didn't all work right out of the box, and I'm not sure why, whether Simon's J's were sort of a slightly different version of IPL or who knows what. Okay, some of them work, some of them didn't. This mostly works. Okay, and let me show you it working. So the first thing I'm going to show you is an Ackermann function, which was the classic example that Newell used. You're familiar with the Ackermann function. It's this really simple math function that explodes when you get up to reasonably small numbers. Okay. And so I actually have the code for the Ackermann function. This is it. I couldn't find it. I have it in Newell's own hand somewhere, like a sheet like this, except it was written out and signed by Newell. I couldn't put my hands on it for this presentation. Anyway, it's a very simple IPL function. Okay. And I actually have it in that LIPL, Lisp IPL. And here it is. It's actually in a file, but I'm going to block out the LT, which we'll get to in a minute, and run the Ackermann function. Here you go. No, that's test the stack machine. Where's the Ackermann function? Here it is. Okay. And then we'll run it. So this just runs Ackermann. Where's my shell? Okay, and we say load. Whoops. This is just in SBCL. Actually, I'm going to restart it because, you know, it's dangerous. There's God knows what the state is still around. Okay, hopefully. Okay, that ran. Now, you might say, well, so what? All right, it's like an Ackermann function. Okay, but watch this. Yeah, I think this is right. No, it's not right. Here, I'll run it the hard way. Come on. Here's Ackermann. We're going to set trace mode to default and set the stack to load. Okay, let's see if this works. And I'm just going to do exactly the same thing again. Start it again. Okay, this is the thing running, all right, in trace mode. This is going to go for, I believe it's 24,000 machine steps before it comes up with that 3. What you might not know about the Ackermann function is that even the small numbers, even though they come up with small numbers, actually take a long, long time to compute, all right? And what we're looking at here is if I stop it, you could see every push and every pop on the machine. And this is what I mean by really understanding what's going on in IPL, right? Is I can stop this and trace it. Now, why do I care? The reason I care is because I have to debug the fucking thing, right? So I have all of this, there's, you know, half my code is the interpreter and the other half my code is the debugging jig, right? This stuff. So this will, I promise you, eventually stop and give you the Ackermann output that it gave you before. All I did, by the way, you saw, I just commented out the turn off the debugging line. But I think it takes 24,000 steps, which we won't wait for. Okay, now I'm going to go back to LT, all right? And I'll show you LT working. Kill this. Start up SBCL again. Get rid of this pile of nonsense. You saw it come up with the answer before. It just took a while because it was going to be 24,000 cycles and just wasn't tracing them. Oh, sorry, I have to change the code. Comment out Ackermann. Oops. Comment in LT. Now, I'm not going to trace LT yet, although it takes a lot shorter than Ackermann. And I'll show it to you. And I should be able to run LT. Oh, did I not comment in LT? I probably didn't comment in it. Yeah, that would be helpful. This is the Steve Jobs moment, like, why did you unplug the last computer to prove you weren't cheating? I'm definitely not cheating here. So that's LT, the real LT really running. Okay, on my interpreter, it was given P, so given A, so the I means implies, it's proving that A or A implies A, and it has a rule that a P or P implies P, so it's just substitution, right? Very simple proof, okay? Turns out I can get 10% of the proofs that they got running working. I could show you a few more of them that work. Many of them fail, and I don't know why, because now I'm at the hard part, which is actual debugging. Right? Instead of debugging my machine, and we're still finding typos in the, you know, in the LT code from the OCR and blah, blah, blah. So I just want to show you kind of the end of this. This is my plea for my cry for help, all right? There is a GitHub repo, and you can see that I started this February 2025, whoops, wherever it is. And then there's a million commits, blah, 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 lots of versions, debugging until April. We're really working on it. And then in June, I actually got to the point you saw there, right? And then the commits are really far apart, and they get farther and farther apart until you basically get to today or a few days ago, right? Where I spend days trying to figure out what the fuck's going on, right? Because I'm not only debugging my IPL interpreter, which was what I was doing earlier, but I'm debugging LT also. That is to say, I have to understand how LT works. And I'm debugging, like, everything's in BCD, and you can't have individual characters. They have to have zeros in front of them, and blah, 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 right? It's like, if you want to, I said I wanted to get into their heads. I'm really in their heads, right? Way deeper than I think I had, I had paid for. But it's fun. And anybody who wants to see this old stuff really run, we've got a list of projects. Once we get the IPL interpreter working, there's GPS, the general problem solver, right? Problem with that one is we actually don't have the original code, although I'm going to Simon's archives in sometime this year in Pittsburgh and Newell's and trying to find the GPS code. So there's a bunch of spelunking in archives and a bunch of really fun hacking in Lisp and a bunch of real frustration, but fun, kind of good fun. I actually like debugging more than programming. I'm not sure I should admit that in this audience, but the debugging, you really have to figure out what's going on. Programming is the LLMs can program, right? They can sort of debug, okay, but if you've really got a twisty bug, you really kind of get your head around what's going on. Anyway, let me see whether I said everything I want to say. I've said a lot of random stuff, but as I said, hopefully this sort of magically coheres into this general concept of getting the earliest AIs running and really getting inside the head of the earliest AI engineers. And I think that's probably all I should say here, and you can ask me otherwise. Thanks. And anyone who wants to, either join the Discord server or, pull the GitHub, fork the GitHub repo, or just contact me and I'd be happy to, work mano with it, right? On it, or hacker on it.
Do you work with the Computer History Museum?
I talk to them. They don't seem that interested. I think they're busy. They're very interested, but not, for example, they won't let me actually see the Simon's J's. They say, oh, no, it's online. You don't have to see them. No, you don't understand. I want to actually see them, right? I want to hold them. There's something about this, like holding the original ELIZA, right? I got to hold the printout. It's literally, you remember the old printout, right? When we opened it up, it was on fanfold, right? I want to show you one other thing. Yeah, don't drop it. Well, I think it's numbered, actually. They did number them. They were that, at those days. In fact, they had autocode to number the decks. All right, any questions other than that? You know who I am. I'm easy to find.
So now that you've gotten the head of these, old time AI people, you say, what would they think about modern AI?
That's a really good question. I have this conversation with other students. Oh, sorry. What would Simon Newell and those folks think of modern AI? And there's two points to that. So Simon was the cognitive scientist and Newell was the engineer. I mean, they were both very smart people. Okay, Simon has a Nobel, in case you don't know this. Newell has a Turing Award, which is the closest thing to a Nobel you can get as a software engineer. I think Newell should have a Nobel also, personally, along with other people. So anyway, it's not a Peace Prize. We talked a lot, but by the way, another thing I'm working on is an SMM, a small math model. Okay, and the reason that we built the small math model is because we actually had all of the pieces. Hinton was a professor at CMU. I used to go drinking with him, even though neither of us really drunk, but at bars in Pittsburgh, he taught me how to flip a cigarette into my mouth, even though neither of us smoked. Anyway, so Hinton was there. Simon, Hinton was like, connectionism, right? Everybody who was sane actually was kind of, let's do whatever works and understand it. The one thing that we would have driven Simon crazy, or Simon and Newell crazy, is we're going to build AIs that are going to replace everybody. Okay. That would have I don't know what the reaction to that would have been, but that was the farthest thing, first of all, because it was insane to think of a possibility, right? Okay. There was Hal. Remember, Hal appeared right after, in 1967, I think, right after ELIZA. Okay, and Minsky was an advisor on HAL, so I'm told. But anyway, although Minsky, as it turns out, I think hated Weizenbaum, blah blah blah, blah, some politics. So you know, we know what Weizenbaum thought about that because he wrote a book, okay, and said, you know, judgment is impossible for these things, and judgment is all that matters, as we're finding out now, by the way. My guess is that Simon would have agreed with that, although they would have all been into actually doing it. Weizenbaum was very against doing it. Simon and Newell and all the sorts were like, let's engineer this thing. We really want to build. But they were doing it. Simon was doing it, and Newell to a large extent to understand humans, not to replicate humans. Okay, so the whole goal there was to understand humans, not to replicate them. You replicate them as a proof of concept of understanding them. Now we don't give a shit, right? It's just basically a big hammer, a very, very useful hammer for many things. I will admit I use it all the time to debug and write little pieces of code. The small math model I referred to was entirely written by an LLM, although I had to do it in little pieces, okay? You know, and guided, as anyone who's done this knows this game. Am I answering your question? Yeah. You had a question. Yeah, we already have something better than human. Next question. Yeah, I mean, it depends. Humans do a lot of things. It's not better than humans in every way, right? I mean, have you ever, one of my day job these days is building methane, basically, you know what a drum drive was? So I built, literally yesterday, I was building a drum drive, but its job was not to do memory, it was to remove methane from the atmosphere. But what was I doing? I was putting tiny little nuts onto boards, right? Okay, that stuff is still impossible. I mean, you can build a machine to do it that's better than human for the tiny little nuts on boards, but if you have to like fit this thing in and figure out where it goes, there's just no fucking way. But they're better than humans at like lots of things, right? They write, they spell way better than I do, right? But somewhat, I mean, these things have balanced our checkbox better than I have forever, right? By the way, it turns out APL under the guise of K is now extensively used in the finance industry. So it still lives. By the way, my very first, I worked on Univax APL interpreter. So I've built the internals of APL also. I've lived way too long, time to die. All right, any other questions? Not, you know where to find, did you have a question? Okay, all right, thank you.